Hello, ladies and gentlemen, and welcome to another wonderful lesson with Mr. Wheezy. Um, this is the last one, seniors. Kind of crazy. Um, but hey, let's get her done. Let's do her. Then you can be done with calculus, except for the quiz. Sorry. Anyway, find the area of the graph with the kickoff here. This is where we're doing all the summation stuff. I'm going to skip this because the first thing we start off with is doing one like this. So why do two of these when I can show you with the one? If you really need to see this, look back to the last lesson, or it's in the filled out version if you really want it. But I'm going to skip ahead just so that we can kind of get into things here. So we have this region here. So it's bounded by the graph of the square root of x. So this is square root of x curving through here. So then we're also limiting it from 0 to 1. So from 0 to 1 on the x. So this way and this here. So we're looking for the pinkish area here and not the white and the blue over here or anything white over here. It's this area and this here. So evaluate the limit of x approaches infinity f of c. And this should be I, not a 1. That is a 1. Never mind. C1. No, it's CI. CI. Change of XI. This is an I. Yes. So CI is the right endpoint of the partition. So the right side, where are we hitting? They're going to give you that. CI is going to be I squared over N squared. And change of X, I, is going to be the width interval. So the first thing we need to find is, well, what is our change of x? Change of x is going to be, well, our right endpoint, which is given by CI. So I squared over N squared minus, well, the one before it would actually be the N minus 1 squared over N squared. So minus 1 squared. I minus 1, sorry. Should be I. Because it's the previous I. Yes, that's how it should be. That's yep, don't go off of this one. So, where this is coming from is the previous interval. Well, it would have been this one right here. So that's the I minus 1. So wherever the previous I was, I being the previous term. I is the term we're talking about here. So if you FOIL this out, you're going to get, well, first off, we can put it all over N squared because we have the same denominator. Common denominator, we can do this. So we have our I squared out front, minus then. Foiling this, you would get I squared minus 2I minus 1. So that would become a plus, this is a plus, this would be a minus if we get rid of that one out here. These I squareds cancel. So what this is going to go to is 2I plus 1 over, actually that should be a minus 1, because negative 1 would be a plus, and when we subtract it, switch back to negative. Sorry. So it's a minus here. Minus 1 over N squared. Alright, so when we set this up, we have our limit as N goes to infinity of the square root of our CI. Our CI is I squared over N squared. So I squared over N squared times our change of x, which is 2I minus 1 over N squared. Well, square rooting, both of these are squared in here, and each could get that square root. So this is really the limit as n approaches infinity of I over N. So we have an n times n squared. So out front we can move the n to the third, 1 over n to the third, because it's on the bottom. Limit as n goes to infinity. I would have to get distributed to each of those. So 2i squared minus I is what we're going to have left on this side. So that's where, if you want to look back at 4.2, where those formulas come in, those summations. So 1 over n to the third, limit as n goes to infinity of, we would have bracket here, 2, and I squared goes to n times n plus 1, 2n plus 1 over 6, minus, we would have I just goes to n times n plus 1 over 2. So this could go to 1, this could go to a 6 right off the bat. I'm also going to get rid of an n and make this n squared, just to help simplify down a little bit. So 1 over n squared, limit as n goes to infinity. So this here we're going to have to FOIL. So n and 2n would make 2n squared. N and 1 plus an n, 1 and 2n would be plus 2n, and 1 and 1 would be plus 1. That's all over 3 and not 6. Wow, sorry. So over here we can minus 2 n and 1. So this is where I probably could have held off reducing those, because now we're going to have to get a common denominator here, which is going to be 6. By the way, these we can put together and get 3n. So 1 over n squared, limit as n goes to infinity. So 2n squared, we're going to have to take it times 2 to make this 6. So all this up top here would be times by 2 again. So we would get 4n squared over 6 plus 3 times 2 would be 6n over 6 plus 2 over 1, or 2 times 1 would be 2 over 6. Minus here would have to take it times 3, so the whole thing would be times 3. So minus 3n over 6 minus 3 over 6. 1 over n squared as the limit goes to infinity. So this is, we're going to do the last steps, so hang in there. So 4n squared, there's no other 4n squareds, so we're going to start with that. 4n squared over 6. I have a 6n minus 3n, which would end up being plus 3n over 6. And 2 6 minus 3 6 would be minus 1 6. So if we distribute this here in, this will get an n squared, this will get an n squared, this will be an n squared. So those can cancel, and this will reduce to 2/3. Here 1 cancels, here none cancels. So as n goes to infinity, this is going to be small over big, which is going to be gone. Small over big, gone. So this is all we have left, which is 2/3. Now, big, long process. So this is what should be the area underneath the curve here. Area under this curve. So that's what that is. So this can find that area under the curve, or we can get into definite integrals. So Riemann sums. So that's where we're going to sum these. And that CI was in between the left endpoint and the right endpoint, and we did all that. So that's that Riemann sum for whatever our change of x is, sort of a thing. So to get change of x, we did b minus a over n to get the width of the largest subinterval. And so it developed it into this here. You know, as that change goes to 0, so as that change gets smaller and smaller, we want to find the sum of all those areas. Well, what that morphs into is that integral here. So we're going to do the integral like we kind of started there with 4-1, except we've added in from what spot to what spot are we covering. So this is going to be the definite interval. It's from here to here and not for the whole spectrum. We have it for certain x's on our graph. So what's that's going to allow us to do? It's going to allow us to find the area underneath the curve in a really faster, easier way. And if you're mad at me for making you do the long way, again, sorry, but it's a good way to kind of see where you're going from. It makes you appreciate the shortcut that much more. So here's how this is going to work. So theorem 4.4, if a function is continuous on a closed interval AB, then f is integral on AB. So long story short is, as long as there's no gaps, jumps, skips, anything like that, we're going to be able to find the integral. So how these work is like this. So first you're going to go through and you're going to find the integral of 2x. So what would this have been? Well, going backwards, we add one of the exponents, so technically this is do the first, so that makes it x squared, or 2 in front, and then we divide by that new exponent, so this is going to cancel, we have x squared. So the integral here is going to be equal to x squared. Now, here you're going to put a little bracket, and we're going to put those other things, so negative 2 to 1. So what that's saying is, okay, this is our integral, now we need to evaluate it based off of this. So you put the top one in first. If I put 1 in here, 1 squared minus, when you put the bottom one in, negative 2 squared. So 1 squared is 1, negative 2 squared would be 4, so negative 3 in this case. So go through, find the integral first, you'll set this up, then go through, do the top number first, put it in, then subtract when you put the bottom number in. So here's another one. Integral here. Well, remember, this is to the first, so we would get 4x squared over 2, which could reduce to 1 and 2. This here would go to x to the third over 3. Now there's no number to cancel, so integral would go to x squared, 2x squared, minus x to the third over 3. Put a little bracket in. We're going to go from 0 to 4. So, start with your top number. 2 parentheses 4 squared minus 4 to the third over 3. And I'm going to put this in a giant bracket. Let's do that. Just so we know they're together. So we're going to minus. Now we do it with the backside. So 2, 0 squared minus 0 to the third over 3. Now, nice thing about this, zeros are going to be 0. They're all going to cancel. So all we got to worry about is this right here. 4 squared. Well, 4 squared is 16. 4 to the third. So it's 16 times 4. 64 over 3. So in other words, this is 32 when we times it by 2. So when you subtract these out, you could get like bases, and what you get is 32 over 3, which in other words would be 10 2/3. So 32, if you put it over 3, I'll do that. Sorry, I kind of skipped that step. We'll give you 96. 96 minus 64, 32. So if we have a single number, when we do the integral, all we have to do is add an x. So this would become 4x, and we're evaluating it from 1 to 3. So 4 times 3, again, I'm going to put that in brackets. We put 1 in there, 4 times 1. Well, this would be 12 minus 4, which is 8. It's so much nicer than doing that long other way. Figured, why not end the year on a good note, something a little more simple. Hopefully you guys all do well with this and you guys don't have too much trouble. So, integral here. X, remember, we get our 2, so we divide by 2. 2 just adds an x, so x squared over 2 plus 2x from 0 to 3. So, these both have, I'll go through it, I won't even jump ahead, sorry. So, bracket, start with the 3, 3 squared over 2 plus 2 times 3 minus, well, we'll have 0 squared over 2 plus 2 times 0. Again, those are all zeros. They're going to cancel out. 3 squared would end up being 9 over 2 plus 6. To get common denominator, this would be 12 over 2. 12 and 9 will then make 21 over 2. So in other words, 10 and 1/2. So that's how those are going to go. Find your integral. So do that working backwards compared to those derivatives. So find the integral and then evaluate. Take the top number, put it in for x, minus out when you put the bottom number in for x. That's all you got to do. Now we do have two special integrals here. If we're going from a to a, so we're not going anywhere, it's automatically 0. You have no width, so you can't have an area if you don't have width. And if you flip over the numbers, it's just negative of what it is. So, like here, if we go from 0 to 3, if we flip it over to go from 0 to, or 3 to 0, we just put the negative in. And so if this is 21 over 3, when it flips, it becomes negative 21 over 3. Just changes your sign. As far as additive interval property here, if we split this interval up, so like from A to a point in between, and then that point in between to the other endpoint to B, just add what you get together, and you're going to get the whole thing. So if we find part area and part area, if we add them together, we get our whole area. Think of it that way. Now, when you're doing this, if there is a constant number, just like when we were doing sums, we could pull that out front, do the integral, and then times it in the end. If we have a couple functions that are being added or subtracted, you can find the integral of each one and then put them together. Again, a lot of like what we did with the sums before. So, integral here. Negative x squared would go to a negative x to the third over 3 plus 4x would go to squared over 2, which should end up being 2x squared because the 2 to the 4 will reduce. The minus 3 would go to a minus 3x. Add that in. So from 1 to 3. So really what that property was allowing us to do is, this one had numbers in front. You can still do the integral here and then deal with the numbers. These are added or subtracted. So technically they're each individual functions, and that's what allows us to find the integral of each one, and then we can put them all together. So that's kind of how those are being used. But if we put these in here, again, starting with brackets. So 3 in there, negative 3 to the third over 3, plus 2 times 3 squared, minus 3 times 3. For the other side, we would have a negative 1 squared, over 3, plus 2 times 1 squared, minus 3 times 1. So if we start simplifying, 3 to the third is 27, over 3 would make it back down to 18, but it was minus, so negative 18. 3 squared is 9, plus 2 would be a plus 18. Those are going to cancel out. 3 and 3 would be 9, so minus 9. We have that yet. 1 to the third is still 1, so 1/3, but it's negative. But this here would make it a plus 1/3. 1 squared is still 1, times 2 would be a plus 2. And 3 times 1 would be a minus 1. Oh, sorry, this would be a minus 2 because of the minus here. The minus 3 would become a plus 3. So, simplify from there. I'll have, well, 9 minus 2. Negative 9 minus 2 would be negative 11. Plus 3 would put you at 8. And then 1/3 there, 2, would end up with double checking my math here. Yeah, we set it up right. Okay, so negative 9, negative 2 would be negative 11. 1/3 and 3, so plus 3 and 1/3, which should knock it back to a negative 8 plus 1/3. So where it's negative 7 and 2/3. But yet I got something different on my homework somewhere if I have a typo there. Oh, yep, I have a typo. That's my bad. No, I don't. This should be 9. That was my bad. I got ahead of myself. That should be a 9, which means that would cancel out as well as with the plus. That's, yep. Wow, I messed up your last lesson. I'm sorry, guys. So the negative 9 and negative 9 would make a negative 18, which could cancel with the plus 18. That's where I went wrong. Negative 2 and 3 would be 1. 1 plus 1/3. You end up with your 4/3. That's what you should have. Sorry. Now we're good. Just last little bit. Theorem 4.8, preservation of inequality. So all that's doing is if we get into inequalities, that still stays the same. So if we know f of x is less than g of x, if you do the integral, it should still be less. So the sign won't change when you're dealing with integrals. That will still, its values will still stay the same. Whichever one's bigger will stay bigger. And that's it. That is it for calculus, guys. Can you believe you made it here? Isn't this awesome? I mean, I'm totally going to miss you guys. Hopefully you miss me. But hey, we're done. We survived. We made it. And that's all she wrote. So, if you guys have any questions, comments, concerns, please pan me. Just know I may not always get to it as fast. So it'll be better if you send me a message on Google Classroom or email. I see that sooner. So that's it, guys. I guess I'll talk to you later.